particular, by the way, what do you think is going to happen if I run time stepping on ODEs that either look like one of these equations or are very close to one that doesn't admit a solution or has multiple solutions? Well, any of the linear solves and so on that we're going to use when we formulate these algorithms are going to become more and more poorly conditioned, and eventually your time step just isn't going to happen. Right? So oftentimes these problems can manifest themselves very concretely when you run these algorithms. So for example, I found a nice compact example of an ODE that has all kinds of really yucky behavior, even though he's kind of innocent looking if you just look at the formula. And that's this one on the board here, which is dy dt equals 2y over t. Now the first question you should ask is, Justin, this doesn't seem legitimate because you can't divide by 0, and here you're giving the initial data y of 0. So why is this okay as a differential equation? Well, I gave you y of 0, right? So I only care about dy dt everywhere except at time 0. So this is a perfectly legitimate differential equation to try and solve. Or is it? So let's try and actually solve this. In fact, we'll apply our favorite methods from AP Calculus to do this, and I'll probably screw it up. So let's see. So we have dy dt equals 2y over t. Right? So, at least formally we can multiply both sides by dt, right? The usual trick here. So you have 1 over t dt, and then over here you'll have 1 over 2y dy, and you integrate both sides. Right? This is the method of separation of variables. By the way, you should know that method, as they write it in AP Calculus textbook, is total BS, right? You can't multiply both sides by dt. But you can go back and prove that bad notation leads to this formula, which happens to be correct. Yeah. Anyway, so what is the integral of 1 over 2y? Well, I think it looks something like c natural log of the absolute value of y. Hopefully I'm right. Yeah, cool. Okay. I should put this in my notes. And then we have, no, it's not right. You guys didn't catch me. So it's 1/2 c plus that. Yeah. And then on the other side, we'll have natural log of absolute value, gosh darn, of t, which we will clean up a little bit. With the evidence. And we can absorb both of these indefinite integrals into this one c. Yeah? So finally, for my last trick, I'll take e to both sides, and what do I get? Well, I get, thankfully, I wrote it right here. I get that y equals ct squared. Is that right? Yes, it is. Because right, you move the 1/2 up here into the natural log, right? So this gets the square root of y. Or in fact, you can move the t over here and get t squared. And then you take e to everything, and the c plus becomes some other constant, big C in front of t squared. Okay. So what did I prove to you? I proved to you, now this is one of those times in mathematics where you have to be careful when you have an if and only if. Right? I showed that if you have a solution to this differential equation, then it must take this form. Right? I haven't shown you that all differential equations admit a solution. I've shown you that if they have a solution, it must look like this. Does that make sense? So in particular, let's consider two cases here. Right? So first of all, suppose that remember I have to give you initial data. I have to tell you what y is at time 0. And let's say that y of 0 is 0. That's perfectly fine over here, right? In fact, you can check very easily that y equals ct squared satisfies our ODE, right? In particular, if I put in t equals 0, I obviously get y equals 0. And if you put in the ratio of 2y over t, you get 2t, yeah? Which is exactly the derivative. Cool. But what's the problem? I didn't tell you what c was. Yeah? In fact, any c will satisfy this differential equation with the initial data that y of 0 equals 0. That's weird. In fact, it totally breaks our intuition for what ODEs should be doing, right? Because what we really think of is that somehow all ODEs should have a unique solution. For the most part, that's true. But in this particular case, it's not. Yeah? Really bizarre. In fact, one thing you should do is draw the slope field of this ODE and see what it looks like. And you'll see that any parabola will fit through this, which is really bizarre. Now, on the flip side, let's say y of 0 is not equal to 0. Did my proof on the board here depend at all on the initial conditions of my ODE? No. Okay, so that means y of t still looks like that, but what is y of 0? Well, anything times 0 squared is 0. So I just showed you that if you satisfy this ODE, then y of 0 equals 0. So there exists initial data for this differential equation that makes it unsolvable. Yeah? Now here's the thing. If I'm writing software to solve this ODE, do you think your software is going to be able to look at this formula up here and check if he somehow has some nice existence or uniqueness property? No. So it is your job as the implementer, or at least the client of this software, to give it an ODE that you expect to have a solution. And sometimes it's not as obvious as you might think it is. So anyway, all this is to say that you need to be a little careful when you talk about solving differential equations. In particular, some of them don't have solutions. For the most part, they do. In fact, we'll mention one theorem in just a moment. But in fact, next week when we talk about PDEs, very little is known about existence of solutions to PDEs in general. And in fact, a lot of times, the best we can do is actually take a PDE, put it into a simulation, and say, well, the simulation behaves okay, so we're guessing it has a solution. It's not a very satisfying answer as a mathematician. Yeah? In fact, if you can show, my PDE professor in college used to explain that, that clay math problem, like one of the big outstanding math problems, is basically to prove that water does not explode in a finite amount of time. Yeah, if you can prove that, then you get $1 million and fame for life, right? And this is called the Navier-Stokes equations. And basically, these are the equations we use to simulate fluid, if like water is splashing around. And certainly, this is a very popular technique and very practical. But we know very little about the theoretical solutions to these equations. Anyway, thankfully, the story for ordinary differential equations is much happier, and there are lots of nice conditions that you can check about this function f. Remember, we have y prime equals f of y. You can look at properties of this function f, and they'll tell you whether or not you have a solution. Right? So I give you a very strong theorem here, which says that if your function f is Lipschitz for any Lipschitz constant, then it has an ODE that has a unique and existing solution for all time. Now this is a very strong condition, right? This is a condition on the slope of f. But if it satisfies such a thing, you're good. And in fact, if it satisfies it in some neighborhood of your initial conditions, right, then you're good for some small period of time at least. Right? By the way, do we all remember what Lipschitz is? We should, because we use this for a fixed point iteration. Remember, a Lipschitz function is one that kind of looks like his slope is bounded, right? The difference of f of x and f of y is related to the difference of x and y with some constant in the front. So if f is Lipschitz, then we're good. Now if we return to the sort of weird, scary ODE that I wrote down here, what do you notice about this function? Well, there's division by t here. And in fact, the slope goes really crazy as t approaches 0. Right? And so this function is really obviously not Lipschitz. Cool? Which is good, because if it were, then they would have a solution. Yeah? Now, if I gave you initial conditions that started at t equals 1, for example, and asked you to simulate forward in time, you'd actually be good, right? Because at that point, everything kind of doles out. Yeah? But the solutions are not as fun. Okay. Right. So now we're going to move into the material that if you have taken an ODE class, you probably haven't worried about quite as much. And the idea here is we want to know what ODEs we can hope to solve. Right? So remember, in this class, we keep cycling back to the same 5 questions about all these different numerical problems. And one of them is this idea of stability, right? Where you kind of want to see, for example, if I perturb my input data a little bit, right? This is what condition numbers are all about. If I perturb my input data a little bit, how do I expect my output to change? Right? So my output now is some simulation of my ODE over all time, and my input is just what? The positions and maybe velocities of my particles at time 0. And it turns out that even when a differential equation admits a solution, right, like even maybe I checked that f is Lipschitz, there are certain differential equations that have really gross properties and make them really unsuitable for the simulation tools that we'll talk about. And in fact, in general, the simulation literature looks at these ODEs and just throws their hands up and says, well, I'm not going to deal with that because there's just no hope here. Yeah? Abandon all hope, all E, whatever. Anyway, so in particular, pacing around. Let's say that I want to solve y prime equals f of y, but as we saw on a couple slides ago, that function f could be really quite complicated, right? But thanks to Taylor and Maclaurin and friends, we can linearize f, and at least to some degree we can write f as locally looking like y prime equals ay plus b. Yeah? And so if we can understand solutions to this differential equation, at least in some neighborhood of time, t equals 0, this will give us some idea of how our ODE integration scheme is going to behave. In fact, we can kind of bound, by looking at the coefficients of f, we can kind of bound our behavior by using this equation. That's some complicated theory. Anyway, so let me make sure I get my substitution right. Yes? Okay. Sorry. Oh, I'm carrying it around. Okay. So this equation, I think you guys could all solve using basically this machinery. But I'm kind of a lazy mathematician, so in fact we're going to do one more substitution and then consider even simpler formulas. In particular, okay, so we wrote y prime equals a y plus b, yeah? And now I'm going to define y bar to be equal to y plus b over a. All right? So then, so what happens here? Well, now we have y bar prime, right? Is obviously equal to y prime, right? And y prime is a y plus b. And now what is y? Y is nothing more than y bar minus b over a. Yeah? So this is a y bar minus b over a plus b. So look what happened. In fact, this is just equal to a y bar. So nothing really interesting happens as this thing depends on b. No? By the way, this little mini proof doesn't appear in any textbooks I could find. It is a question you should ask, which is, okay, you said that this is a first order approximation, but you threw away a constant term, and a constant term affects the derivative of y. It's not like it's just truly a constant. So you do have to do your homework and make sure that you haven't lost any behavior. But in fact you haven't, because really secretly what's going on is that y is just a shifted version of this y bar that satisfies a very simple equation. So hopefully you'll agree with me. So, what have I done? Well, I took what could be a humongously complicated equation and I wrote down possibly the simplest ODE you could hope for, right? Y prime equals ay, and we're going to solve him instead as kind of a proxy for understanding the full equation. Yeah. So in particular, I'll get rid of the bars because I don't feel like it. And let's solve this equation really quick. Do I need to solve this again? It takes like 2 seconds. Okay. Right, so we have dy dt equals ay. So in particular, using our abusive notation once again, we have 1 over ay, which we'll assume a is non-zero for now, times dy is equal to dt. We'll integrate, yeah? So that means that you get, see, and this is where I'm going to get it wrong after all. L and naturally value of ay equals t plus constant. Is that right? Okay. But if I take the derivative of this, then I get 1 over this times. This is embarrassing. Yeah, so we get 1 over ay times a. So you're going to need like that. Okay. Cool. You guys should help me. This is math that you should know, just because your instructor is up here talking his face off. Okay, so in particular, then you can, I'm going to just keep absorbing constants into the c, so you get ln of mod ay is equal to at plus c. Right, so if you take e to both sides and kind of absorb this other a, then you're going to get y equals some constant c e to the at. Okay. That shouldn't have taken as long as it did. I think I've lost my mathematician license in this class any number of times. Anyway, cool. So, now that we have this solution, right, the nice thing now is that this nice linearized equation, has a solution we can just write down, and then we can look at these solutions and try to understand what they tell us about life. Now, probably the simplest And I claim that there are three cases you should worry about here. The simplest is when a equals 0, right? What is our ODE in that case? Well, this is y prime equals 0. So what does solutions to this guy look like? It's pretty darn simple, yeah? So this is time, and this is y, and there's your initial data, then it's just a bunch of straight lines. Yeah? Because it says y doesn't change. Obviously, solutions to this equation are very stable. Now, from a CS205 point of view, the question that we're going to ask is what happens if I take, remember, what is my input? It's y of 0. If I take my y of 0 and I perturb him a little bit, then what does this tell me about perturbations of my ODE as time moves forward? It tells me that they neither get better nor worse. Right? That is, that this distance is the same as that distance, is the same as that distance, and so on. Right, so if a equals 0, then my equation is certainly stable, and my equation isn't any worse, my error isn't any worse than at time 0. Yeah? You can probably see where I'm going with this. Now if a is negative, right, then this looks like a minus exponential, right? So we have different initial starting points. All of these guys kind of look like that, right? We're down here, they'll look like that. Yeah? So in fact, these differential equations have a really nice property. Right? What is this property? This says if I get my initial data a little bit wrong here, what happens over time? All my solutions actually get closer to each other over time. So if I screw up my initial data here, in fact, over time, my mistake gets canceled out. Right? This is a great property to have for a differential equation. We call it a stable ODE, and in fact, most ODEs have this property to some degree. Yeah? Now, contrarily, what happens when a is positive? Well, it's still an exponential, right? So this is the a less than 0 case, this is the a equals 0 case. We have a third case, sorry, my board use is a little messy today, where a is greater than 0, and now they're still exponentials, but they're going away. Okay, this is the a greater than 0 case. So what happens here? Well, if I screw up my initial data, even by just some little itty-bitty epsilon at time 0, then pretty soon, that little tiny bit of mistake that I made at time 0 is going to be amplified any amount. Any amount that you desire, it will be amplified if you go far enough in t. Right? This is a horrible property for differential equations to have, because what it means is that even if like the mistake that I made was IEEE like floating point rounding or something at time 0, that little itty bitty amount of mistake I have no hope of recovering from. In fact, the job of ODEs like this in life is to make that error bigger. Yeah, as you can see, well, if I do this better, you can see that the distance vertically, grows as you move forward in time. These equations are unstable. In fact, they're particularly unstable when your initial data is about 0, right? I can have very close solutions that are gathered about 0, and in this case, this guy's going to wing off to infinity. In this case, this guy's going to wing off to minus infinity. These are two very different solutions, right? So in fact, numerically, we say this is the worst possible conditioned case, and one that we really just won't deal with in this course. And thankfully, there are very few, this sort of corresponds to a positive feedback loop, which thankfully does not occur in nature very often. Right? Usually we have things like springs. Right? Springs are a nice second order model of physics. And springs have this nice property, right? Where if I overshoot a little bit with a spring, it's going to pull me back together, right? And if I undershoot, it's going to push me back out, right? So springs are very stable. These guys are not. In fact, I'm challenged to come up with different models that actually look like this. Although apparently some of these global warming things kind of do, which is a little scary. Okay, so in multiple variables, we've actually already seen this, and we talked about eigenvectors. Remember, now a linear equation, by following sort of the same substitution here, we can show that a linearized version of our ODE is y prime equals ay for some matrix A. Okay? In particular, if we take our initial data, y of 0, and write it in terms of the eigenvectors of y, right? We're going to say ayi equals lambda iy, then we have a closed form solution for the solution of this equation. Yeah? Which is that you basically solve the ODE, right? You use this formula in each of the eigenvector directions. Yeah? By the way, if you don't remember how this proof goes, you should go home and try and prove it on your own. It's a good little exercise for some of the eigenstuff we've done. Yeah? Remember, at least when A is symmetric, these eigenvectors are orthogonal, so somehow all of these behaviors decouple. Great. So what does this tell you? This tells you that if we understand stability in each of the eigenvector directions, then really we've characterized stability of our ODE completely. Right? So in fact, the stability theory for ODEs, at least the sort of simple stuff, is no more difficult than studying e to the AT and then just remembering that this just happens in all the eigenvector directions independently. Right? So usually theorems about stability of ODEs will talk about the spectral radius of a matrix, and if you'll recall, I think we've defined this in this class, but in case we haven't, the spectral radius of A, right? We usually write rho of A is equal to max, the max magnitude of any of its eigenvectors, or values. Yep. And in fact, this is true even if A is asymmetric. It's easy to prove that all matrices have at least one eigenvector. Cool. Right, so again, the stability of your ODE depends on the maximum eigenvector, which is nothing more than the spectral radius. It's called the spectral radius, again, because spectrum is a word you should associate with eigenstuff. Okay. So I guess in the remaining 15 minutes, we're probably a little earlier. The remaining couple minutes of this class, maybe not. I'll decide. In the remainder of today's lecture, we will, and for all of Wednesday's lecture, we're going to formulate different schemes for integration. And when I say integration here, what I really mean is moving these ODEs forward in time from the initial data. By the way, do you see why it should be called integration? Right? You have y prime equals f of y. So if you want y of t, basically we're taking the integral of both sides. Yeah? The problem is just on the right-hand side, you have an unknown inside of your integral, so you don't really want anything. Yeah? Okay, so today we're going to cover two very simple strategies called forward and backward Euler. How many of us have seen these before in some content? I feel like these are more familiar than some of the other things we've covered, which is good. You guys could use a break. It's been hard in this class. Anyway, so forward Euler, I claim, is sort of the easiest possible integrator to come up with if, like, somebody held a gun to your head and said, come up with a forward time integrator for an ordinary differential equation, you'd probably say forward Euler. And the reason is that it's sort of a very reasonable scheme. So basically what forward Euler says is that, well, f is only more than an approximation of the slope of my function, so let's just use it as the slope, right? Multiply it by dt, and I'll get the next y. Right? And in particular, let's be a little more formal about this. So let's say we have f of yk. By the way, we're going to say that yk is the thing at time tk. Right? We'll define tk equals t0, which I guess I've pretty much taken the initial time to be 0, but nothing really changes. Plus, we'll say h times k. So h is going to be the spacing between all of our time steps, and k is going to be the number of time steps we take. Okay, that's my notation. Cool. So remember that our ODE that we're trying to solve is y, y prime equals f of y. Yep. But now, from our last lecture, right, conveniently all of these things are going to dovetail in a nice way. From our last lecture, we know that this is nothing more than yk plus 1 minus yk divided by h, right? H is going to be our time step today, plus big OH. Right? Is there a square there? I forget. No, there's not. Okay. Cool. So what am I going to do? Well, I'm gonna remove the middleman here and solve this guy for yk plus 1 because he's the unknown, right? And it turns out everything else here is known. Other than the higher order terms. But what are you going to do? Yeah? So in particular, if we multiply both sides by h, then we get hf of yk. What's y? I guess I could have done this in more than one steps. Yeah, whatever. Order h squared now, right? Because I moved an h out. And right, and now if we reshuffle a little bit, you get yk plus 1 equals, and we'll move this yk over here, plus hf of yk plus big O of h squared. And this term is going to be more defined. Okay, so what does forward Euler does? He says, well, let's just ignore this last term and time step using this formula. Yeah? In other words, this thing gives us the slope of a line. I'm going to draw a little line segment and just keep moving forward. Yeah? This method is called explicit. What that means is that given yk, I can find yk plus 1 with very simple machinery. I don't need to solve any equations, nothing. I just plug yk into this function f, and out comes my next iteration. Yeah? It's going to be different from our time step in a second. And as we just showed, we call the error in this method the truncation error, right? Because effectively I just wrote a Taylor series and then I truncated it, right? I removed the higher order terms. So we say that locally, right, in a single time step, we have quadratic, or order h squared, localized truncation error. And now, this is a little bit of just convention in the world of ODE, but usually we say that the number of time steps that we're going to use looks sort of like 1 over h. Right? In other words, this sort of makes sense, right? As the width of your time step gets smaller, you expect to have to do more time steps to get to the same place in time. Yeah? And so, in particular, you've got to do order 1 over h of those. So we say globally, if we run this scheme, right, for all those time steps, then we lose a power of h in the process, and we have that this is an order h error kind of accumulated over time. Well, this global truncation error. Right? So forward Euler is a first order accurate method. Cool. Now forward Euler, in fact, I'd say is probably the most common ODE integrator you find in everyday life, but has a lot of really terrifying bad properties that we have to watch out for. In particular, let's go back to our model equation. Right? Remember, we like to think about these time-stepping methods in terms of what they do to y prime equals ay, and thankfully for us, we can just write down what it does and work it out in detail. Yeah, so, okay if I erase again, it's because I screwed it up. Okay. So let's say that we're solving y prime equals ay, our favorite equation. And we're going to assume that a is less than 0. We're in the stable case. Right? Otherwise we're kind of hosed even from a theoretical perspective, and obviously these methods are going to be very poorly. So, right. So if we do that, then if we use forward Euler, then we get yk plus 1. Well, remember that if we go back to our scheme here, right? He's going to equal yk plus h times f, right, which is nothing more than a yk. Yeah? So in particular, this is 1 plus h a yk. Very simple way to get there. So you could say that you know, applying this inductively, you get that this is the same as 1 plus h a to the k times y0. Okay. By the way, would I actually use forward Euler to simulate this equation in real life? No, I know the answer to it. This is just for sort of theoretical purposes, to characterize how it's behaving. Yeah? So in particular, now that we have this, for our method of integration to be stable, which is not the same as the ODE itself being stable, right? For this method with a positive amount of time in my time step to not explode, I had better have that the absolute value of this number here is less than 1. Right? Because then what's going to happen is over time it's going to just converge to 0, whereas if this the absolute value of this is greater than 1, it's going to amplify y0 over time. That make sense? Cool. So if we do that, I'm writing too big. We can work out the stability of forward Euler. And what do we get? Well, we know mod of 1 plus HA less than 1, well that's the same thing as minus 1 less than 1 plus HA is less than 1. Yeah? So if we subtract 1 from both sides, minus 2 less than HA less than 0. Now A is a negative number. This is a gotcha. Right? So if I divide everything by A, then I have to flip the inequalities in the process. Yeah? So and then we get 0 is less than H is less than you can say this is minus 2 over A or 2 over mod A, because A is negative. Cool? What does this tell us? Well, it tells you, by the way, these are all if and only ifs. Yeah? Okay, so this says that I'm trying to solve a stable ODE. Remember that I assumed back all the way at the beginning of this that A was negative. So I know in the back of my head that the solution to this equation is going to have this nice decay property that we already drew on the board. Right? But now I wrote down the forward Euler time step, and I showed that in fact, the solution that I get out of forward Euler isn't always stable. That if I have h, my time step is too big, then it can still explode. Right? So in particular, we have something called a time step restriction. This says that we cannot use forward Euler if we want to take steps bigger than h in time. Yeah? Now remember, what does A look like in the multidimensional case? He's sort of the smallest eigenvalue of your matrix. Or rather the biggest. No, the biggest, smallest. Smallest. Biggest, yeah. If A is the largest eigenvalue of your matrix, because you're looking at the spectral radius, right? Then your time step is limited by 2 over the biggest eigenvalue of that matrix. Right? Now sometimes, for example, the protein folding problem that I mentioned at the beginning of class is known as a stiff ordinary differential equation. And the reason for that is that the different eigenvalues of this matrix are on very different scales. Right? So for example, if I have a very strong force that's coupling these things together and they're wiggling back and forth in a very tight way, then that eigenvector is going to be very large, that eigenvalue, right? Because that sort of represents a very high frequency in time. Whereas, some very low frequency sort of big pull between 2 ends of the protein is going to have a very, very low eigenvalue, right? Because this takes a long time scale before anything interesting happens. Right? So this ODE is stiff because you have this big variety of different eigenvalues in your matrix. And stiff ODEs have this really irritating problem, which is that your time step is limited by the biggest eigenvalue, which could be very large if you have this very tight behavior between adjacent molecules. Right? So in general, we say that forward Euler is not a good method for stiff ODEs, because what's going to happen? You're going to take itty bitty little time steps to satisfy this restriction for all of your eigenvalues. Right? Because if A is big, then you're going to do that. Even if most of your eigenvalues have this sort of large scale behavior, you're governed by the weakest link, and otherwise your solution will explode. That's not a good property to have, yeah? So, right. To solve this problem, and this will be the end of our story for today, and then we're going to notice next time that in fact there are far more complicated and useful solutions here. We're going to introduce a method called backward Euler, which is probably exactly what you guessed. Where now, instead of using the forward derivative approximation that we introduced at the beginning of our discussion of derivatives last time, we're going to use backward derivative. Yeah? Now, from an order of accuracy point of view, this is going to give us the same thing. If you recall, both of those have the same error, as they sort of should, right? They're symmetric about 0. But in fact, this strategy is going to be far more stable. So again, if we want to derive this method, we'll say, we don't know yk plus 1, right? But if we did, we could evaluate f there, right? And we know that that's the same as y prime at time k plus 1. Yeah? And if we write down our backward difference approximation from k plus 1, you're going to get yk plus 1 minus yk, all that over h, right? Plus O of h. And if you solve this guy for yk plus 1, just like we did before, you get this formula here. Now, you guys should notice that something kind of funky happened when I did this. Okay? Which is that I have a yk plus 1 on both sides of this formula. Yeah? So how do I get the k plus first time step? Right, this value of yk plus 1 from yk. I have to solve this equation to get that value. Right? So in fact, if I use a method like backward Euler, it's called implicit. Right? Because yk plus 1 appears on both sides of this equation, and we have to find the y that satisfies this relationship. Hopefully this makes sense. We'll do a concrete example in a moment. Right?